All right, welcome to the third session in the casing design part of TPG 4242 Drilling Engineering 3 or Advanced Drilling Engineering. Today is February 1st. Of course, a little bit bad weather during the night, so a little bit reduced class. But if you don't mind, I will record this class too. And eventually I'll be able to post this in a way that you guys can look at it again. Today we are going to cover probably what many would call the essence of the class. Stepping back to what we have covered, basic material science in the first lesson, double lesson, and then in the second double lesson we went through like an introduction to the basics. If you guys want, I can very quickly share this presentation with you guys if that's gonna help you, or I can do it in the session recess. Yeah. Sorry, I could not send it in advance. I know some of you like to print it and note on it. That will have to be for the next time. Yeah, so the introduction part, we went through land-based wells, how you make the well pad, how you and well site, and how you start spudding a land well, and many of the subsurface considerations for how to put up a casing program, like an outline of it. And we went a little bit more into detail with regards to subsea systems. Showed a video where a full wellhead Christmas tree system was compiled. The third class here, we're going to cover the basics of the casing design method. We'll go through the acting forces. This is how you would actually systemize the approach. You get a hold of a lot of subsurface data. They are given to you from the subsurface team. And then what we do is set up what we call extreme cases through the whole life cycle of the well. Anything from producing the well, shutting it in, running gas lift, injecting in it, killing it, any well interventions like scale treatments, pumping scale inhibitor, if it's fractured, now or later if it's converted from a producer to an injector, if it's like an alternating water alternating gas injection. All these things you need to know them, and then you set up cases, and in the industry these are predefined. In most of the softwares you'll find that there's a comprehensive set of these cases, specifically extremes, where you do the analysis, and then you get the curves coming out in so much that on one side you have the acting forces, on the other side you will have the strength of the tubulars, which is point 2. Understanding the strength of pipe. We made the basics when we talked about the basic material science and the manufacturing of the pipe. We'll get back to that part a little bit towards the end of this session 3 casing design process, as we call this. And then analyzing the result, understanding that these curves, what the strength compared to the load, understanding what we are looking at, knowing that yes, this is good, or no, that's good. Part of what we need to understand would be wear and tear of casing. Casing wear typically comes from rotational pipe. Say you install an intermediate casing and you drill the next section. You will have some work done inside the installed casing, and it will get worn from this. Also, well interventions later on, they will do some wear and tear, and you have also sometimes corrosion coming in. If there's time, I'll show you guys the basics of corrosion in materials. That would be at the end of the class. It's optional. It will only be for your benefit, and it's not part of the curriculum of this class. Yeah. Regulations, they are important for you to know what we made in this at NTNU, not for this class, but for the one that we used to have in the autumn, where we model a full well using the same procedures and steps as in the industry, and also the same software that they use. We had a class like that every autumn earlier, as said in the introductory class for those who were there. And for those who want to have a peek, I could share the governing documentation that we made for those classes. Yeah, so that you have an understanding. You will get a peek, an extract in this class. Remaining sessions and absolutely not covered today. Pipe properties, manufacturing of pipe, standards for manufacturing of the pipes, and standards for the strength of pipe. We're just gonna. That's a very short part since we have covered what it is earlier. But the standards, the API and the ISO standards for this, and a little bit also the NORSOC standard for it, but is useful to know what they are, how they are built up, and what they say. We are going to cover that briefly so that you have an overview. And then there's going to be a session in itself looking at the differences from the what the industry is using. And as said in the introductory class, the very first one, that modern calculation techniques, they are a lot more accurate. Yeah, we'll get into that later on. And again, another optional topic would be how we do well and field development, if there's time. Yeah, and this is just point 3 again. We're here looking at a casing. As said in the previous session, we do an open hole design and a casing design when we are modeling our wells. We need both designs to be okay. The open hole design is a very brief thing. It's just during the operation, whereas the casing design is for life cycle. Yeah. We call it very often just kick tolerance, the open hole design. It needs to be within limits that we discussed in previous class. The extract from the governing documentation of NTNU. We're talking here about a kill margin and a point that is going to be. Yeah, I think this question has been put in absolutely every exam so far. Section design pressure. It's something that you guys as drilling engineers will be asked. And section design pressure. If you look at the drawing, and we imagine that on top of this well there is BOP. The section design pressure would be anyone can imagine what a section design pressure would be if you are going to explain that. Yes, it's based upon the formation pressure, and it's based upon the formation pressure in the from the open hole planned in that section. Um, and of course, it says here on the first full red box, gas filled casing. Now, that would be the gas that comes from the formation in a situation where you have had an incident. Typically, the load case, and I will always now talk about load cases. There's different scenarios through a well's life cycle, and part of the well life cycle is of course drilling it, not just the call it 5 to 25 years producing after, depending. Um, so in this case, section design pressure only pertains to when we are making the well, drilling the well with a BOP. And the section design pressure is the highest pressure that you can encounter during the whole time you're drilling that section until you install your next casing or a production liner or whatever it would be that you are putting in. So cover the open hole and change covering the open hole will change the pressure regime in the well, and you have to do another calculation, right? Yeah. So the principle of gas filled casing limited to fracture. This is very essential to understand. I'll make a very quick drawing so that there can be no misunderstanding. It's in fact very simple. We have the casing on our open hole. We have some pore pressure at some point here that will yield the highest pressure in the well. And of course, what we have at the shoe is a fracture gradient. Yeah. You can fill this casing. I'll go with green is the best color on a green board. You can fill this casing to the top with gas. That's what you can do. But you cannot exceed the fracturing pressure. If you try to go higher in pressure here, then you will just fracture the shoe here. The casing just doesn't need to be any stronger than the fracturing gradient here for this purpose, right? And in many situations, that is the case. Let's reflect back to what we talked about in the last session, and we make another drawing here. Let me see if I can find more colors that would be useful. Yeah. No. Then we just say that the cement is up here until here. All right. And you have also a fracturing gradient here. And what's going to happen in this annulus, gas gradients and so on, you will not see a higher pressure between these two than the fracturing gradient in this annulus, because you have not cemented into the casing. All right. So basically, this is how you think about well integrity and integrity for these casings, starting from already this point. Now, this section design pressure only is as simple as when you go to those operating the rig. They would ask you what is the section design pressure, because they want to test their BOP to this pressure and no higher. And for us, what we do as engineers, as said, we only follow this principle, but pressure max would I get on top here. And basically that's the fracture gradient, and I try to put up the pressure from the weight of the fluid itself. To simplify things, I always say that the density of gas is 0.15, like this, and then it will be the height here. So you deduct that part from the fracture pressure at this point, and you will have the maximum pressure you'll see. Now, as it says here, yeah, but SG. Thank you for the question. Let me see. 0.27 it says in this extract from the governing documentation. Kill margin. Now, the highest pressure from the nature is what we described, but should you be in this awful situation that actually the whole casing is full of gas, right? Which is it's not normal, but again, a load case is an extreme, and it's a design point. We need to go to the extreme to know that yes, it can hold it, right? So in that case, we need to bullhead back, kill the well, push all the gas into the formation. That's what we need to do. So we call it the kill margin, and in governing documentation there are specific margins in pressure that you add on top to this number. So the section design pressure is this plus kill margin. And for the larger sections, typically shallow, they are around 15 bar, and then going a little bit deeper, they are 35 bar. Yeah. Don't know if this is readable at all on the recording. Maybe not, maybe not. Yeah, zoom in. Yeah, go ahead. Fluid. It's the fluid itself, and it's gas. We always use gas because that's worst case, right? And it's a definition. What density does a gas have? It would change, right, with pressure. But we have to say something, and this is what you can use as drillers. If you go to production guys and to those who model and simulate, they will say that's a simplification. Yeah. All right. So this is an extract on how we have to use governing documentation in our casing design to find part of this is a combination of the load case gas fill casing, and your option is limit to frac at shoe. Now there will be other design options. You don't need to limit to frac at shoe. There could be special cases where you're allowed to do other things. You when you play around in one of these uh, softwares for casing design, you'll see that there are alternatives. But in most operators, they would ask you to use this criteria for gas fill casing and the pressures that follows from it. Again, small variations. They would tell you that the kill margin may be 20 bar and 40 bar for the deeper ones, and so on and so forth. But the principles, they are very, very similar, the governing documentations of the different operators. Yeah. Yeah, injectors, it says in the bottom here, is you have to consider two things: shut-in pressure. That now we're talking purely about the kill margin, right? You can't just use gas fill casing and a certain amount there, because injectors, typically if it's a water injector and it's yeah, filled with water, then you need to consider what is my shut-in pressure. Yeah, you may not fracture exactly at the shoe for that case. Yeah, so you need to look more into it. Calculation example: the fracture gradient is set to 1.5 SGs, and for this case, the shoe is at 1,050 meters. The pore pressure at the bottom is 1.45 SGs, and that's at 1,700 meters. And we always assume gas, and again, the example here shows us that it's 0.15 SGs. Here would be more or less all the input that we're going to need, in addition to the given governing documentation input. This section is intermediate, and if we just step quickly back, we'll see that the intermediate here would be 1338. Casing and liners with surface casing function OD less than 16 and 3/4 is 35 bar. Okay, so we now know that for the section design pressure, we have to add the 35 bar. For the load case gas fill casing limited to frac at shoe, it will be different. You guys want to make a quick calculation and for yourself, or do you want to just see the solution? It's very simple stuff, but it's what you're going to do at your exam also. Anyone have an answer? So the fracture gradient is 154 bars. And we're going to limit that to the frac there. The density of the gas and the gas column itself is 15.5 bar. Which means that the surface pressure will be 139 bar. And we had, well, in this case they said 15, but it's 35 in the governing documentation. It depends on the casing size, I guess, and that's not really specified here. So it could be either 154 or 20 bar more if it's larger than 16 inches. Yeah. Very simple, very straightforward for you guys. I believe anyone wants to have a look at this, it will be in the presentation, and I will make that available to you guys. If I don't have your email, please send me one so that I can reply to you and give you the presentations. I believe 5 of you guys did that after the first session, so they have a copy of the compendium and a copy of the 2 first presentations at least. And that's how we have to do it until I get my user back and established. Yeah. Yeah, and this is just to say the impossible case where you have gas pressure from the bottom all the way, and we know that's not going to happen because it will fracture the shoe. Yeah. Why is it not likely to be a problem? Because it will fracture the shoe, as we talked about. Yeah.
You mean a scenario where the case in reverse instead of the shoe fracture?
Yes. There is a potential for that. Um, then your input numbers needs to be wrong as I see it. I'm trying to figure a way how the weaker formations in the shallower in the open hole section would not be accessible or plugged in a way. Um, During normal drilling, we have mud. Mud is supposed to close off any leakage, right? It contains pore plugging material. That's what we add to mud. It doesn't work in shale formations because shale doesn't really have pores as per se. They are so small that you can actually theoretically drill a shale without any pore plugging material. Um, and some of the very tight a shock that I had, well, not shock, but something that was very different when I started drilling in outside of Norway was that formations they are so tight that you can kill a well with water, or just brine that is a little bit heavy, right? So you pump it down and it doesn't leak off, whereas the permeability in so many of the Norwegian wells that I've been working on, absolutely 90% of them at least, it's so high that if you pump a brine, it's just going to fall into the well and equalize with the pore pressure, and then the well is going to start to mix in its reservoir fluid, and you're in trouble. You haven't really killed the well, if you see what I mean, right? Um, uh, but looking at it, thinking that okay, so we have a, a leak off in a weak formation just below the shoe that we know is going to take um, a certain limit, and then say that that formation is plugged off for some reason, and you get into a much higher pore pressure below than you ever got numbers for, say. And this again would be something valuable to take away, I guess. Um, if you have a well next here, drill, and it's supposed to be an injector, it's perforated here, and there is a formation that is supposed to go below into and support the reservoir for that well, but it has fractured up, so it goes here, right? Then you're in trouble. Also, if you drill a producer into a formation that has injection support, there are different things to consider. It's the effect of the temperature. The temperature will go down. All injection will cool down the formation, and it will make it much weaker, less competent. So there are a number of things to consider when you do these things. That's not part of the curriculum, but it follows. Call it what I'm thinking when you are asking a question. Yeah, I'll take another question and I will get back to you. Yeah.
You say that you use brine in other countries. What do you use
In other countries where I've been drilling, we used brine to kill the well. We have to use stuff with pore plugging material, for example, mud. So you bullhead, and typically what you do in these wells that are producing hydrocarbons, you would use a cushion of base oil. Base oil would swallow the interface, if you see what I mean. If you try to push back what is in the well, you will always have a little bit of mixing in the front, right? And the base oil is very, it absorbs gas. So you pump some base oil and then you go over to mud. It could be oil based or it could be water based, doesn't matter. As soon as the mud itself hits the formation, you will see a huge spike in the pressure. Yeah. Going into when you sit in the operation and you watch these things, I find that really cool to be honest. You see first the base oil hit the formation and the pressure goes a little bit up, and then the mud comes and it's like pew, straight up. Yeah, it really works, the plugging. Yeah. Yeah. Getting back to your question, I want to say no. When we as drilling engineers design, we don't normally get a burst pressure during the next operation. That's why we are doing the design. But of course, there are special cases. There are. I could also think about the casing not being in spec. Let's say that you have a casing installed there with a certain wall thickness and something has happened to the casing, or during your operations, this one is probably the best answer. You have a problem and you have to sidetrack, and you sidetrack yet again, and you forget to recalculate your casing wear and what the casing actually is able to withstand. Then that's probably the most likely scenario. Yeah. Here is a list of all standard load cases. These load cases comes from the governing documentation of NTNU, and they are a little bit more comprehensive than the list you'll find in the north of D10. And you see here, there's a difference between all the pipings. Some of the cases and scenarios are not valid for all the different scenarios that we're talking about. Displacement to gas, we don't do that for a conductor, or basically surface casing. We don't. Yeah, we have to do it for the surface casing. As we talked about for the open hole design, the kick tolerance. We don't do kick tolerance unless we have a BOP, right? Because we are not closing in the well. And here's the same thing too, displacement to gas. You can't really displace the well to gas unless you have a BOP, right? So that is a logic part too. Pressure testing. I like to ask you guys questions so you think and take away learnings. And I'll ask you something about pressure testing now. Why? What is the definition of pressure testing and reason for doing it? Why do we do pressure testing? Yep. Yeah. We that is the call it the one side of the coin. The one side of the coin is to just see that we have achieved sealing. Okay. Now let's add a little bit more to it. What determines the level we are going to when we pressure test? Let's say section design pressure is such a case. This because we are testing the BOP, right? Let's say that in our case, we came up to this being a larger than 16 inches casing, so it was 154 bars. That was the section design pressure, right? That is our level. Why do we test to 154? Why don't we test to 130? Why don't we test to 170? Yeah. Yes. Yes, exactly. To to determine that the most extreme case is covered. And yet again, our BOP and our well, we are afraid of it. Why? These are very valuable components that are going to last for hopefully decades, right? So we don't want to go to 170. We go to what we need to. So that's why we design and we know exactly what we're doing. We don't give the margin after it says 35 bar, let's do a 50 instead. We don't do that, right? They care for their BOP, the guys in drilling, and they don't want to test it more than necessary because on one side testing it wears it down just as much as you really need that BOP in a critical situation, right? So that's the other side of the coin of pressure testing. Yeah. Okay. Low case number 2, pressure testing supposed to be the curve. if we let's try this. When we are seeing our curves, this is the depth, and this is very often the load, right? Going horizontal this way. Here is where you want your pressure test, and all the other curves you want them on this side, right? That's what you need to know. And sometimes with drilling mud, it's very heavy, so you'll end up doing some strange stuff to know that the shallow parts of the well, because a gas filled casing has a very high pressure here. How are you going to test that with mud? It's going to look really ugly, right? You have to go to 154 bar here, and the density of the gas is like this, right? Whereas with mud, it will go something like this. So you have extreme pressures in the bottom, pressure testing for this. Yeah. Green cement test. I think we are. Yeah, we can manage that one. Green cement test. Anybody been in operation and know what it is? Did you say this one here? The third low case is called green cement test. Basically, it's the same as the pressure test of a casing. I will revert back to the thing said in the very first class when we were looking at how steel forms into grains, and I said cement does the same thing. Cement goes from liquid phase. More bored to draw. Okay, cement goes from liquid phase to solid, like this, and then grains form into it, like this, and it goes from liquid to solid in typically anything from 3 to 6 hours. It depends on your design, your composition, and everything else that you have. And typically the strength as it starts to become solidified is the same as you guys have experienced when you have been at the beach. You hold the sand in the beach and you can form it as a snowball, right? Yeah. And that's the cement when it is solidified but not entirely set up. It builds strength and it bonds, and it's only able to take any load after the setup time, designed to be anything from 3-4 hours to 6 normally. Yeah. So we call it a green cement test because the first hour after the cement is pumped into place, it is completely wet. And when you pressure test a casing, what does it do? It balloons. We'll look more into it, but it balloons quite a lot. And it makes it shorter because you're ballooning. Say the sand that you hold, the wet sand from the beach, like this, and you let it go, and you can see your finger imprinted on it, right? You can see that where your fingers have been quite clearly. Imagine that you pressure test after 2 hours when the cement is like that sand. It never goes back and fills the void. What's going to come down there? The liquid from the top comes down, and you have channeling, and there's no bond between your casing and the cement, or the cement and the formation. You ruined it. Green cement test means that you're pressure testing within the hour after placing the cement, and you're cementing. You're testing to the same level as the pressure test. Yeah. The only difference would be that you have basically a different liquid situation in the annulus. That's it. If you wait until the cement sets up and you do the regular pressure test, then it's hard cement on the outside. Now, cement, normally a compositional cement, unless you have a very special composition, like Crete and or these nitrogen cementations, cement density, would be 1.7 to 205 SGs in between there, right? Very heavy. Whereas the moment that it starts to set up, after 1 hour, up until it's set up, we say that cement has a density of fresh water. 1.0. Yeah. So that's something to think about. Yeah. For once, on time, I'm not going to steal from your recess. We'll go and talk through a little bit more of these ones. I think the rest is quite straightforward.